class. I already graded the project and I sent it to you. So I don't know if you, if anybody did not. I mean, I thought that there is one group that did not submit, but then it turns out that they submitted their project, and I'm gonna mark it and then send it to them. There was one group in the other section who submit the project. I graded it, but I have to email each group for privacy's sake, and it was very hard job for me to put the email for every student in the group. We have 20 or 23 groups, and then send the 23 emails to 3 and 2 students together. But if by chance you did not receive an email, let me know, okay? Because it seems like I missed one group from the other section, and I send it to them. Also, before we start, I got the feeling from some of you that you don't know what's a screw jack. So I thought I should show it to you. This is a real example of a screw jack, just for changing a flat tire. And this is a schematic or a sketch, which is showing you how we operate the screw jack to raise the car up. Interestingly, also, I am here going to show you the patent, which was registered in, sorry, this is the patent which was registered in very long ago, 1920, okay? For probably, maybe it is the first, I don't know if it is the first screw jack. And this is another one in 1949. So this is an kind of an improved version of it, different design maybe, and but this is just to show you a screw jack. I thought this is going to be interesting for you. But today, what are we going to do? We are going to continue the discussion on the power screws. We should have started the problem, but with the other section, we could not finish it. Actually, we just stopped in the beginning of it. So let's just start and see where we can go here. Let me just... Student asked to extend the deadline for the homework until midnight. I did so I hope you know about this right now. So what did we do? Basically, or what are we going to do is we are going to focus on one single thread, okay, on the power screw. We will assume that this is a square one, and we will make an analysis of all forces acting on that thread for two conditions. The first one, okay, the first one is for raising the jack, or let's say the bolt or the load, and the other one is for lowering. And as you know, friction is always going to oppose the motion. So for lowering, the load PL is the lowering load, and it will be opposed by the force friction multiplied by N, which is the normal force. Here we have the force, and this is the normal force. And in here, the force is still up. You didn't change things. The car is still there if you are talking about screw jack. But here you are lowering. So you are raising the car. And for that, you will see that this is PR, and the friction is going to go down. And of course, here we have the value of the normal force. Now, if you look, this is the lead. We talked about the lead is how much the screw will advance in the nut if you rotate it by one rotation. And this one is the like the circumference, right? It is by D. The circumference is 2 by R. So here it is like the diameter, the radius is d over 2, and then you have pi dm. Okay. Now, if you do the equilibrium equations, which we're not going to discuss, you will end up with the raising torque equation as this, and sorry, the raising load and the lowering load as this. We are interested mostly on the torque, and for that reason, we will convert the load into torques, and this is the final equations. Now, we have TR, the raising torque, and we have TL for the lowering torque. Now, let me tell you this. If you look and just reason carefully, you will see that this dm, the diameter multiplied by pi, is going to be a big number compared to the lead. They are not comparable. Okay, I mean, it's not, you will never get that the lead is going to be bigger than by dm. Okay, the lead is a small distance, which is traveled 1-2 millimeter, whatever, but by d is the circumference, it's going to be big. So if you analyze the lowering torque and the raising torque, you will notice something which is very, very important. Let me focus on the denominator first. If you look at the denominator of the lowering torque, you will find it to be pi dm plus the friction multiplied by the lead. And this is just two numbers, positive number, because it is dimension. Friction is never negative. So you will just add two numbers, and the denominator is going to be positive. Good. If you go here, you will also notice that the denominator will be positive. Why? Because the friction is usually small, 0.3, 0.2, 0.1. Even if you put oil, the friction will get even smaller. And if you put a very rough surface, the friction is going to go high, but it is still going to be in the fraction of 1. And in the end, what happened? When you multiply the friction by the lead we just said that it is a small, you will get a small number. And this small number will never be bigger than pi dm. Can you imagine pi is a 3.14? Just say 3. And then you multiply it by the diameter. There is no way that then the denominator will not be positive. It will always be positive. So for the raising torque, the denominator is positive. The numerator is adding two values, which is going to be positive. That's why the raising torque is always positive. Good. Now, what is risky over here is this. Look at the lowering torque. The lowering torque in the numerator, you have pi multiplied by f multiplied by dm. Now, although you take the diameter and you multiply the diameter by 3.14, but if the friction f, the small f, is very small, let's say 0.01, then this magnitude will drop down significantly. Yeah, and if L by any chance is a little bit big, like 2-3 millimeter, maybe, I don't know, you may get in a condition where this value becomes negative. Now, what does it mean to have a negative value? What does it mean? I don't ever think it is about clockwise, counterclockwise. Huh? Here we have magnitudes. We don't have directions. So the concept of a clockwise, counterclockwise doesn't apply. We are calculating magnitudes. So let me make it very simple. If actually you get the coincidence where this is just wait a second, ya shabab. If by coincidence, ya shabab, give me one second. Okay, if by coincidence this numerator became 0, let's not talk about negative, it became 0. What does it mean? The lowering torque is 0. يعني معناها you need 0 torque to lower the car. What is 0 torque يا شباب? In reality, what is 0 torque? Anybody?
Nothing.
Freely moving.
What was it, يا محمد?
That it will freely moving.
Yeah. Maybe a little breeze of a wind will nudge the car, and then it will trigger the lowering process by itself. You don't need to apply torque to lower the car. خلاص تورطنا. What happened? You raise the jack up, you leave it, it goes down by itself. This is very dangerous. Or if it is close to 0, it might just stay like that for a little bit, and then suddenly it falls down. And thus, our safety net here is to go to the numerator of the lowering torque, say that by F dm minus L must be greater than 0. If it is not greater than 0, we are in big trouble, which means that by F dm should be greater than L. This is known as the self-locking condition. And I talked to you about self-locking last time, and there I am talking to you about it again. So what we need to do whenever we design a jack or a screw or whatever that carries a load, we need always to focus on this self-locking condition. The self-locking condition is satisfied when by F dm is greater than the lead, period. Now, the next thing that we talked about with regard to the power screw is the fact that they are very, screw jack is an exhausting little machine. If you have a flat tire and you use a screw jack, there is no doubt that you will just be exhausted, and especially in the weather of Saudi Arabia. Now, it turns out if you calculate the efficiency, okay, which is, by the way, the efficiency is F by the lead divided by, which is the T0, divided by the raising torque. Why? Because usually raising torque is higher than the lowering torque. So if we want to measure the real efficiency, we need to measure it with the difficult one, not the smaller one, not the easy one. And it is no surprise, you will see when we solve the example, that this this coefficient of efficiency is going to be 25, 30. Now, if it is 30, ya shabab, it means you need to put as much as 3 times the effort to actually raise the car. In reality, if it is 100% efficient, then you will put this much power, let's say 100 watt, and because it is not efficient by 30% only, you will have to put how many? Nearly 3 times that. And it is no surprise, that's why everybody hates it, everybody gets exhausted and tired whenever they change the tire. So it's very interesting that the numbers will speak the reality, okay? Now, the thing that we talked about in the beginning, just beginning of the lecture, is we said that, I don't know honestly if I said it, but if I didn't, all of the formulation that we did was for a square thread. Now, if we look at the power screws, we told you they come into a square mechanism, a shape or geometry, and they also come in acme shape. Now, with respect to acme, we know in here, we know that the force is going to act perpendicular, okay? But because the thread is inclined, if you remember, this is the thread like this, and we have lambda as the lead angle, and then the helix angle psi. Now, in here, we will have also the angle. If you remember, this angle, we called it 2 alpha, right? And this 2 alpha is the angle of the acme thread. Now, so here we will have the both lambda and alpha coming together. However, since lambda is small compared to alpha, okay, the analysis has been done without regard to lambda. So lambda was ignored. And it turns out, you need to listen very carefully here, that the lowering torque and the raising torque will change as follows. You know the friction term? If you go back here, do you see the friction terms? I'm gonna clean this up. This one is the friction term, and this one is the friction term in the raising torque. This is the friction term, and this one is the friction term in the lowering torque. So if you, this is for squared threading. If you have an acme thread, the only thing that you need to do is to go to the friction terms, these terms, and multiply them by secant alpha. That's it. So if you go to the raising torque, you will see that this is the friction, and that's secant alpha. This is the friction, that's secant alpha. The lowering torque, you go to the friction part, you multiply it by secant alpha. Now, what you need to understand as a takeaway here is that, remember this note, remember that the above equation is approximation because the effect of the lead angle lambda has been neglected. Okay, it was neglected. Now, what you should know is that in general, this is a very nice hint for practical purposes, that for power screws, ya shabab, the acme thread is not as efficient as the square thread. Square thread is more efficient because of additional friction to the wedging action, this wedging. However, it is often preferred because it is easier to machine. It can allow for other practical reasons like split knot and so on. Okay? Now, what is important here, before we start the analysis for the stresses acting on the power screw, is that sometimes for practical reasons, we need to add a collar. Now, what is a collar? Look, if you fix here, if you fix the nut over here, you hold the nut, and then you power the screw. You rotate the screw, you connect the screw to a motor, for example. In order to elevate, load, you raise them up, down, you will need to put this collar. Look, the collar here is act like a physical place where the load can sit on, and then you can raise it up or lower it down. Now, of course, if I tell you, look, this thread, and this thread are always in friction with the nut. And this has been taken care of by the, and then this is taken care of, we took care of it in the raising torque and the lowering torque. There is a friction. That's something we considered. But this part, if you look in here and look in here, This one is also going to rotate. And as it rotates, this platform in the top, okay, might be fixed, or if it is not, still this is going to rotate. And if the platform doesn't rotate with this, there will be friction. And so you need to add more work. For that reason, there is a torque for the collar. So if you have a collar, you add this torque. Look at the torque. TC, the torque for the collar, is equal to F, which is the load that you are carrying, multiplied by FC, the friction for the collar, multiplied by the diameter of the collar, divided by 2. Now, if you have a collar, you need to add this torque. If you don't have a collar, you don't need to worry about it. Do you understand? Now, the next step is to analyze all possible loads that generate different kind of stresses within the thread. Now, I think, ya shabab, I will be tired and I will repeat this 1,000 times, and I believe you will never get it right. Many of you. So help me out here. I want you to understand it very well. What are we going to do is we're going to look at the thread, ya shabab, كأنه الثread like this. The square thread, okay? And this is the diameter like this. كأنه عندنا one thread. It's a cantilevered beam. Just like that. Now, what happened? We know that there is another thread below coming from the knot. صح ولا لا؟ هما واحدة thread واحدة فوق thread. Let's look at two threads only. Now, and then there is the load, F, which is the weight of the car, for example. Now, we know that this load is going to be transmitted to the thread, and the other thread is going to act in the opposite direction. And now we have the entire mess, right? All kinds of forces and action. Not only this, but our screws rotate, and because of the friction, there is going to be torque, and the torque will cause twisting, so it will generate shear stresses. Now, listen to me carefully. What are we going to do? We are going to find out all the stresses that are generated on the thread. This is very tricky. Why? Because when we say this, we're not talking about critical location. And we're not. We're talking about the entire thread. Here, قطعة كذا, and there are forces on it. Each force will generate its own stresses. Later, we will tell you, we want to know if the thread is safe or not. And interestingly, the question has a different answer. يعني, let me try to explain it as much as possible, okay? Just think blindly. If you have the screw, it's a cylinder, and there is a thread on it, okay? This diameter is called the root diameter, the smallest diameter, the distance from here to there. The mean diameter go to the middle of the thread, and the big diameter go to the most furthest part of the thread. Now, if you look, tau is equal to 16t divided by pi d cube. This is the shear stress generated because of applying a torque in a cylindrical part. Now we know that d is in the denominator. The smaller the d, the higher the stress. So logically, if I want to calculate the stress, the shear stress, I should consider the shear stress generated in here. Look, not the shear stress with the part of the thread. Why? Because that's the smallest diameter. This diameter is dr. And for that reason, we use this equation. Now, what is this stress? This stress is the stress generated in the cylindrical part, uniform cylindrical part of the power screw. We are not talking about the threads, huh? not the threads. Now, the other type of stress, which is what? It is the normal stress. Very simple, force over area. Now, in order to make it a better, يا أخوان, again, this is the body of the thread, and the thread is sitting here. I am plotting the thread as a beam, just for example, but the thread is circling around, okay? I don't know even how to do it in 3D, it's very hard. So what are we doing here? The force F is acting on this area. So, very simple, this area is pi over 4 dr squared, and that's what we did. We took the force, we divided it by the area, pi over 4 dr squared. Good. Okay. Now, also, it is practically, in general, the case that power screws, when they are subjected to this compressive loading while they are rotating, they fall in the category, in general, in the category of short to intermediate beams. So buckling of the power screw could be a possible cause of failure. Now remember, buckling by itself is failure. Yielding by itself is another failure, okay? So if it is, in general, short or intermediate, we should use Johnson equation as we did before, and you should worry that if you want to calculate the area, you should use dr, okay? But in general, we are not going to focus on buckling. But in reality, if you have a very long beam, maybe it is going to be Euler, we don't know. But buckling could be an issue. Now, but in general, in our analysis, we are not going to focus on buckling, okay? But this is a possibility. Now, what is the other stress? The other stress is the bearing stress. Why? Bearing stress comes from where? From an area, a finite area, applying a pressure on another area. And what do we have here? We have a thread like this, and then we have another thread underneath it, right? And the blue one is pushing in the black, and the black one is pushing on the blue. Now, in order to make the distinction, we are going to call the bearing stress sigma capital B. This is the stress which is expressed as, طبعا البيرنج ستريس يا شباب دائما نيجاتيف. هو عباره عن area تضغط على area، خلاص مجرد انك you apply pressure it means it is compressive. So what is it gonna do? It's closing. Okay. So what happened? It is always negative, and its value is 2f divided by pi dm, the mean diameter, multiplied by nt, and p. Now, the p يا شباب نعرفها. It's the pitch. If this is the thread, the distance from the beginning of the top one to the bottom one is the pitch size. Right? Now, what is NT? NT is called the number of engaged threads. Now, if we go back over here, okay, we can easily recognize that there is 1, 2, 3, 4, 5, 6, 7 threads. There are 7. But this one, number 1 and 2 and 3 and 4 are engaged. Engaged يعني يا شباب engaged يعني باللهجة احنا ندري نحن خاطب يعني. This is when you say somebody engaged يعني في شخص رجل خاطب له مرأة. But here engagement means they are, you know, in action, in contact. So you may say that NT is equal to 4, which is very reasonable. The number of engaged threads is 4. Yes, yeah, Muhammad.
How about the second thread?
Where is it?
This
one. No. This is just a little part of it is not engaged, so I'm not gonna care about it. Okay. So you can easily say that the number of engaged threads is 4, but don't worry, we have a long story here. Now, if you put NT equals to 4, nobody is gonna tell you no. But what I want to warn you about is that this is not what we are going to do. احنا ناس معقدين ونحب التعقيد. Nothing is easy, right? That's what we do. No, this is not the story. The story will become very clear and you will appreciate it more later, okay? But if you assume that the number of thread engaged is whatever between the knot, that's not wrong. However, we are not gonna do this. Why? It's gonna be clear in a minute, okay? So don't worry about it. So this is the bearing stress. Now, what is the other stress? Of course, if we cut a cross-section and we look at the thread from the side and there is a force acting on it, then reasonably you can argue that this is going to cause the thread to bend. Just like a force. This is a cantilevered beam and the thread is a tiny little beam subjected to transverse load and it is bending. Why not? So this is now, we are going to call it sigma B. B is a small, different than the capital B, which is the bearing stress. Now, sigma B is equal to 6F divided by dr nt multiplied by B. I mean P, not B. What is the last thing? The last thing is to think about the thread with the force. And as we all know, if you have an F like this, this is going to cause a shear force V, which is the same as F. And if you have a shear force, you know that you can use the equation, which is what? VQ over R IT. And then you can think that the shear stress in the thread here is going to be 0. In the bottom is going to be also 0, but in the middle, tau is going to be maximum. So we are always interested in the maximum stress. And thus, since this is a square in general, even for Acme, ya shabab, the geometry of the area here, even for Acme, is still rectangle. And that's why it's fair enough to assume that the maximum shear stress is equals to 3V over 2A, which is the maximum shear stress for a rectangular geometry. What is this? What is this? This is equals to 3F by dr nt multiplied by P. Now, you don't need to worry a lot about those equations because you're either going to have the book or you have a formula sheet. So I am not worried about you not to memorize them. This is actually very easy. I want you to understand them. Why? Because what we said is all possible kind of stresses. Some of them are acting in the middle. Some of them are acting on the top, like bending. Bending is maximum here, positive, and here, minimum, negative, right? But we know that bending in the location of tau is going to be 0. So we did not worry about this. And this is why I told you just earlier that you're probably not going to understand this. I'm trying so hard so you understand it. We can ask you in the exam or in the homework or in the quiz, find all stresses acting on the thread. يعني أي نوع من stress acting on the thread. The thread is big thing. I didn't ask you about a buoyant. خلاص. You go find all the stresses. you find, look, you go find number 1, tau, number 2, sigma, number 3, bearing, number 4, bending, number 5, direct shear. These are all the stresses acting within the thread. But if I tell you I want to know if the thread is safe or not, what is this difference here? Safety. To do safety analysis, ya shabab, we need one single point or multiple points. It's okay. If you have 1,000 points, it's okay. You can write a computer code and you can find the factor of safety at 1,000 points. The question is, are the stresses, all of them, are going to be acting on those 1,000 points? No. No. So if you look at the thread, ya shabab, we are going to establish a coordinate system. And I hope, ya shabab, that everybody in the class will stick to this coordinate system, okay? So we will assume that this direction, which is the outward normal of the thread as x, the axial direction of the bolt or the screw is y, and then using the right-hand rule, positive system, you will have the z coming out. Now, if you plot this like this, ya shabab, this is x, y, and z. In reality, okay, you can just imagine that this is the cross section, and the thread is here. Now look what happened. There are stresses which are, you know, going to be maximum. Like, for example, we all agree that bending at this point, I'm just waiting for the point to appear, over there, this point, is going to be maximum stress. Maximum. This is when the thread is started to bend down. And we know also that torsion, when you have a twisting, is, let's assume that this is the direction, is going to be maximum. Let me write it in green. Maximum here, maximum here, maximum here, maximum here. So that point has a maximum bending, which is going to go in this direction as a stress. And it has a maximum shear, which is going in the outward normal, right? And usually, whenever we have maximum bending and maximum shear, we say, what? That's it. That's our point. And now, in order to assess the safety, we are going to pick that point. That point is called the root. The root of the thread. What are the consequences, Ishwa? In هنا هذا البوينت, bearing stress doesn't mean anything for it. Right? V equals to, tau equals to 3V over 2A. Doesn't make any sense because it's 0 there. And for that reason, look what happened. If we use this system at the root, we will have the normal, the bending stress, sigma x. This is the bending stress. Tau xy is actually going to be 0. The shear will act in the direction of what? Y, Z. Okay? And the normal stress, which is going to act like this, is in the Y direction. So it's sigma Y. What is sigma Z? We don't have a sigma Z. What is tau ZX? We don't have tau ZX. And I want you to remember one thing, that you should always use this convention. مشكلة الطلاب شنو؟ إنه يجي ويروح يسوي له هو coordinate system, and those stresses get mixed up. This convention system, the location of the stresses, this is bending, sigma x is bending, tau yz is the torque, the shear coming from the torque, and sigma y is coming from the normal stress, has been established
دكتور ما في صوت.
So why I told you that the number of thread engaged should not be the same as the number which is the for thread engaged between the nut and the screw. The reason is this: it was proven experimentally, ya shabab, that there will be one thread which will take 38% of the load, and then the thread below it will take 25%, and then the thread after it will take 18%. And surprisingly, the 7th thread will have zero load. So what are we going to do? Since we are interested in safety, we are always going to take F as 38% F, which means we are focusing on the thread which is carrying 38% of the load by itself. And then we substitute NT as 1. Okay, this is what we are going to do. So we'll solve example, inshallah, next class. For now, I will kindly ask you to turn on your webcam. We have only 1 minute. Let's take the attendance, ya shabab, okay? Please. Okay, Hussein?
Yes.
Let me see. Okay. Saeed Saleh?
Yes.
Adnan?
Yes.
Madan? Muhammad?
Yes, here.
Saleh Sultan?
Yes, doctor.
Ali?
Yes, doctor.
وليد العمري؟
Yes.
فيصل؟
موجود دكتور.
اوكي علي؟
Yes, دكتور.
محمد؟
Yes, doctor.
مفلح؟
Yes, doctor.
فهد؟
موجود.
فيصل attended with the other. مصلح؟
Yes,
زير؟ سلمان؟
موجود يا دكتور.
فارس؟ اوكي خالد؟
Yes, doctor. Yes.
سعد؟ سعد؟ سعد is not here. عمر؟
Yes, doctor, I'm here.
تامر؟
Yes, doctor.
مصطفى؟
Yes, doctor.
فواز؟
Yes, doctor.
أمجد؟
Yes, here.
فيصل؟
Yes, doctor.
محمد؟
Yes, doctor.
ناصر؟
Yes.
عبد الرحمن؟
Yes, doctor.
عمر؟ عمر؟
Yes. Hello.
Yeah, I can see you. محمد؟
Yes.
مؤيد؟
Yes, doctor.
محمد. Okay, thank you so much, Ashima.
Yes, doctor.
Doctor,
Yes,
I'm sorry, Saad Hazma here, doctor.
where you Saad?
The mic doesn't work. I don't know what's that.
Okay, thank you so much, Ashima.